The following is a conversation with Scott Aaronson, his second time on the podcast. He is a professor at UT Austin, director of the Quantum Information Center, and previously a professor at MIT. Last time we talked about quantum computing. This time we talk about computational complexity, consciousness, and theories of everything. I'm recording this intro, as you may be able to tell, in a very strange room in the middle of the night. I'm not really sure how I got here or how I'm going to get out, but Hunter S. Thompson saying I think applies to today and the last few days and actually the last couple of weeks. Life should not be a journey to the grave with the intention of arriving safely in a pretty and well-preserved body, but rather to skid in broadside in a cloud of smoke, thoroughly used up, totally worn out, and loudly proclaiming, "Wow, what a ride." So I figured whatever I'm up to here, and yes, lots of wine is involved, I'm going to have to improvise, hence this recording. Okay, quick mention of each sponsor, followed by some thoughts related to the episode. First sponsor is SimpliSafe, a home security company I use to monitor and protect my apartment, though of course, I'm always prepared with a fallback plan, as a man in this world must always be. Second sponsor is 8 Sleep, a mattress that cools itself, measures heart rate variability, has an app, and has given me yet another reason to look forward to sleep, including the all-important power nap. Third sponsor is ExpressVPN, the VPN I've used for many years to protect my privacy on the internet. Finally, the fourth sponsor is BetterHelp, online therapy when you want to face your demons with a licensed professional, not just by doing David Goggins-like physical challenges like I seem to do on occasion. Please check out these sponsors in the description to get a discount and to support the podcast. As a side note, let me say that this is the second time I recorded a conversation outdoors. The first one was with Stephen Wolfram when it was actually sunny out. In this case, it was raining, which is why I found a covered outdoor patio. But I learned a valuable lesson, which is that raindrops can be quite loud on the hard metal surface of a patio cover. I did my best with the audio. I hope it still sounds okay to you. I'm learning, always improving. In fact, as Scott says, if you always win, then you're probably doing something wrong. To be honest, I get pretty upset with myself when I fail, small or big, but I've learned that this feeling is priceless. It can be fuel when channeled into concrete plans of how to improve. So if you enjoy this thing, subscribe on YouTube, review it 5 stars on Apple Podcasts, follow on Spotify, support on Patreon, or connect with me on Twitter at Lex Fridman. And now, here's my conversation with Scott Aaronson. Let's start with the most absurd question, but I've read you write some fascinating stuff about it, so let's go there. Are we living in a simulation?
What difference does it make, Lex? I mean, I'm serious. What difference?
Because if we are living in a simulation, it raised the question, how real does something have to be in simulation for it to be sufficiently immersive for us humans?
Mm-hmm. But I mean, even in principle, how could we ever know if we were in one, right? A perfect simulation, by definition, is something that's indistinguishable from the real thing.
But we didn't say anything about perfect. It could be imperfect.
No, that's right. Well, if it was an imperfect simulation, if we could hack it, find a bug in it, then that would be one thing, right? If this was like the Matrix and there was a way for me to do flying kung fu moves or something by hacking the simulation, well, then, we would have to cross that bridge when we came to it, wouldn't we? Right? I mean, at that point, it's hard to see the difference between that and just what people would ordinarily refer to as a world with miracles,
What about from a different perspective, thinking about the universe as a computation? Like a program running on a computer. That's kind of a neighboring concept.
It is. It is an interesting and reasonably well-defined question to ask, is the world computable? Yeah. Does the world satisfy what we would call in CS the church Turing thesis.
Yeah.
That is, could we take any physical system and simulate it to any desired precision by a Turing machine, given the appropriate input data, right? And so far, I think the indications are pretty strong that our world does seem to satisfy the church Turing thesis. At least if it doesn't, then we haven't yet discovered why not. But now, does that mean that our universe is a simulation? Well, that word seems to suggest that there is some other larger universe in which it is running, right?
Right.
And the problem there is that if the simulation is perfect, then we're never going to be able to get any direct evidence about that other universe. We will only be able to see the effects of the computation that is running in this universe.
Well, let's imagine an analogy.
Mm-hmm.
Let's imagine a PC, a personal computer, a computer. Is it possible with the advent of artificial intelligence for the computer to look outside of itself to understand its creator?
Mm-hmm.
I mean, that's is that a ridiculous analogy?
With the computers that we actually have, first of all, we all know that humans have done an imperfect job of, enforcing the abstraction boundaries of computers, right? Like you may try to confine some program to a playpen, but, as soon as there's one memory allocation error in the C program, then the program has gotten out of that playpen and it can do whatever it wants, right? This is how most hacks work, most viruses and worms and exploits. And, you would have to imagine that an AI would be able to discover something like that. Now, of course, if we could actually discover some exploit of reality itself, then, then this whole, then in some sense, we wouldn't have to philosophize about this, right? This would no longer be a metaphysical conversation, right? This would just be
But that's the question: is what would that hack look like?
I have no idea. Peter Shor, the very famous person in quantum computing, of course, has joked that maybe the reason why we haven't yet integrated general relativity in quantum mechanics is that the part of the universe that depends on both of them was actually left unspecified. And if we ever tried to do an experiment involving the singularity of a black hole or something like that, then the universe would just generate an overflow error or something,
a blue screen of death.
Yeah, we would just crash the universe. Now, the universe has seemed to hold up pretty well for 14 billion years, right? So my Occam's razor kind of guess has to be that it will continue to hold up, that the fact that we don't know the laws of physics governing some phenomenon is not a strong sign that probing that phenomenon is going to crash the universe, right? But, of course I could be wrong.
But do you think on the physics side of things, there's been recently a few folks, Eric Weinstein and Stephen Wolfram, that came out with a theory of everything. I think there's a history of physicists dreaming and working on the unification of all the laws of physics. Do you think it's possible that once we understand more physics, not necessarily the unification of the laws, but just understand physics more deeply at the fundamental level, we'll be able to start, part of this is humorous, but looking to see if there's any bugs in the universe that could be exploited for, traveling at not just the speed of light, but just traveling faster than our current spaceships can travel, all that kind of stuff.
Well, to travel faster than our current spaceships could travel, you wouldn't need to find any bug in the universe, right? The known laws of physics, let us go much faster, up to the speed of light, right? And, when people want to go faster than the speed of light, well, we actually know something about what that would entail, namely that, according to relativity, that seems to entail communication backwards in time. Okay, so then you have to worry about closed time-like curves and all of that stuff. So, in some sense, we sort of know the price that you have to pay for these things, right?
Under the current understanding of physics.
That's right. We can't say that they're impossible, but we know that sort of a lot else in physics breaks.
Yeah.
Right. So now regarding Eric Weinstein and Stephen Wolfram, like I wouldn't say that either of them has a theory of everything. I would say that they have ideas that they hope, could someday lead to a theory of everything.
Is that a worthy pursuit?
Well, I mean, certainly, let's say by theory of everything, we don't literally mean a theory of cats and of baseball but we just mean it in the more limited sense of everything, a fundamental theory of physics, right? Of all of the fundamental interactions of physics. Of course, such a theory, even after we had it, would leave the entire question of all the emergent behavior, right?
Yes.
To be explored. So it's only everything for a specific definition of everything. Okay, but in that sense, I would say, of course, that's worth pursuing. I mean, that is the entire program of fundamental physics. Right, all of my friends who do quantum gravity, who do string theory, who do anything like that, that is what's motivating them.
Yeah, it's funny though, but I mean, Eric Weinstein talks about this. It is. I don't know much about the physics world, but I know about the AI world, and it is it is a little bit taboo to talk about AGI, for example, on the AI side. So really, to talk about the big dream of the community, I would say, because it seems so far away, it's almost taboo to bring it up because it's seen as if the kind of people that dream about creating a truly superhuman level intelligence, that's really far out there people, because we're not even close to that. And it feels like the same thing is true for the physics community.
I mean, Stephen Hawking certainly talked constantly about theory of everything, right? I mean, people, use those terms who were, some of the most respected people in the whole world of physics, right? But I mean, I think that the distinction that I would make is that people might react badly if you use the term in a way that suggests that thinking about it for 5 minutes have come up with this major new insight about it.
Yeah.
Right.
It's difficult. Stephen Hawking is not a great example, because I think you can do whatever the heck you want when you get to that level. And I certainly see like senior faculty, that at that point, that's one of the nice things about getting older is you stop giving a damn. But community as a whole, they tend to roll their eyes very quickly at stuff that's outside the quote unquote mainstream.
Well, let me put it this way. I mean, if you asked, Ed Witten, let's say, who is, you might consider a leader of the string community and thus, very, very mainstream in a certain sense, but he would have no hesitation in saying, of course, they're looking for a unified description of nature, of general relativity, of quantum mechanics, of all the fundamental interactions of nature, right? Now, whether people would call that a theory of everything, whether they would use that term, that might vary. Lenny Susskind would definitely have no problem telling you that, if that's what we want, right?
For me, who loves human beings and psychology, it's kind of ridiculous to say a theory that unifies the laws of physics gets you to understand everything. I would say you're not even close to understanding everything.
Yeah, right. Well, I mean, the word everything is a little ambiguous here, right? Because, and then people will get into debates about, reductionism versus emergentism and blah, blah, blah. And so in not wanting to say theory of everything, people might just be trying to short circuit that debate and say, look, yes, we want a fundamental theory of, the particles and interactions of nature.
Let me bring up the next topic that people don't want to mention, although they're getting more comfortable with it, is consciousness. You mentioned you have a talk on consciousness that I watched 5 minutes of, but the internet connection was really bad.
Was this my talk about, refuting the integrated information theory?
Yes,
which was this particular account of consciousness that, I think one can just show it doesn't work. But
so let me
much harder to say what does work.
What does work? Yeah.
So
let me ask. Maybe it'd be nice to comment on. You talk about also like the semi-hard problem of consciousness, or like almost hard problem, or kind of hard.
Pretty hard problem, I think I call it.
So maybe can you talk about that, their idea of the approach to modeling consciousness and why you don't find it convincing? What is
Yeah.
it, first of all?
Okay, well, so what I called the pretty hard problem of consciousness. This is my term, although many other people have said something equivalent to this. Okay, but it's just the problem of giving an account of just which physical systems are conscious and which are not, or if there are degrees of consciousness, then quantifying how conscious a given system is,
Oh,
right?
awesome! So that's the pretty hard
Yeah,
problem.
that's what I mean by
That's it.
it.
I'm
That
adopting it. I love it. That's a good ring to it.
And so, the infamous hard problem of consciousness is to explain how something like consciousness could arise at all,
Yeah.
in a material universe, right? Or, why does it ever feel like anything to experience anything, right?
Yeah.
And so I'm trying to distinguish from that problem, right? And say, no, okay, I would merely settle for an account that could say, is a fetus conscious? If so, at which trimester? Is a dog conscious? What about a frog? Right?
Or even as a precondition, you take that both these things are conscious. Tell me which is more conscious.
Yeah, for example,
That's
yes. Yeah. I mean, if consciousness is some multidimensional vector, well, just tell me in which respects these things are conscious and in which respect they aren't, right? And, and have some principled way to do it where you're not, carving out exceptions for things that you like or don't like, but could somehow take a description of an arbitrary physical system and then just based on the physical properties of that system or the informational properties or how it's connected or something like that, just in principle calculate, its degree of consciousness, right? I mean, this would be the kind of thing that we would need, if we wanted to address questions like, what does it take for a machine to be conscious, right? Or when should we regard AIs as being conscious? So now this IIT, this integrated information theory, which has been put forward by Giulio Tononi and a bunch of his collaborators over the last decade or two, this is noteworthy, I guess, as a direct attempt to answer that question, to to address the pretty hard problem, right? And they give a criterion that's just based on how a system is connected. So it's up to you to sort of abstract a system like a brain or a microchip as a collection of components that are connected to each other by some pattern of connections, and to specify how the components can influence each other, like where the inputs go, where they affect the outputs. But then once you've specified that, then they give this quantity that they call phi, the Greek letter phi. And the definition of phi has actually changed over time. It changes from one paper to another, but in all of the variations, it involves something about what we in computer science would call graph expansion. So basically what this means is that they want it, in order to get a large value of phi, it should not be possible to take your system and partition it into two components that are only weakly connected to each other. Okay, so whenever we take our system and sort of try to split it up into two, then there should be lots and lots of connections going between the two components.
Okay, well, I understand what that means on a graph. Do they formalize how to construct such a graph or data structure, whatever, or is this? Because one of the criticism I've heard you kind of say is that a lot of the very interesting specifics are usually communicated through like natural language, like through words. So it's like the details aren't always clear.
It's true. I mean, they have nothing even resembling a derivation of this phi. Okay, so what they do is they state a whole bunch of postulates, axioms that they think that consciousness should satisfy. And then there's some verbal discussion, and then at some point phi appears. Right. And this was the first thing that really made the hair stand on my neck, to be honest, because they are acting as if there's a derivation. They're acting as if, you're supposed to think that this is a derivation, and there's nothing even remotely resembling a derivation. They just pull the phi out of a hat. completely.
So is one of the key criticisms to you is that details are missing, or is there
But
something more fundamental?
that's not even the key criticism. That's just a side point.
Yeah,
okay.
got it.
The core of it is that I think that that they want to say that a system is more conscious the larger its value of phi.
Yeah.
And I think that is obvious nonsense. Okay, as soon as you think about it for like a minute, as soon as you think about it in terms of, could I construct a system that had an enormous value of phi, like, even larger than the brain has, but that is just implementing an error correcting code, doing nothing that we would associate with, intelligence or consciousness or any of it? The answer is yes. It is easy to do that. Right. And so I wrote blog posts just making this point that, yeah, it's easy to do that. Now, Tononi's response to that was actually kind of incredible. Right. I mean, I admired it in a way, because instead of disputing any of it, he just bit the bullet. In the sense, he was one of the most audacious bullet bitings I've ever seen in my career. Okay. He said, okay, then fine. This system that just applies this error correcting code, it's conscious. And if it has a much larger value of phi than you or me, it's much more conscious than you or me.
Interesting.
We just have to accept what the theory says, because, science is not about confirming our intuitions. It's about challenging them. And, this is what my theory predicts, that this thing is conscious and, or super duper conscious. And how are you going to prove me wrong?
See, so the way I would argue against your blog post is I would say, yes, sure, you're right in general, but for naturally arising systems developed through the process of evolution on Earth, this rule of the larger phi being associated with more consciousness is correct.
Yeah. So that's not what he said at all. Right. Because he wants this to be completely general. Right.
So we can apply it to even computers.
Yeah. I mean, the whole interest of the theory is the hope that it could be completely general, apply to aliens, to computers, to animals, coma patients, to any of it, right?
Yeah.
And so he just said, well, Scott is relying on his intuition, but I'm relying on this theory. And to me, it was almost like, are we being serious here? Like. Okay, yes, in science, we try to learn highly non-intuitive things, but what we do is we first test the theory on cases where we already know the answer, right? Like if someone had a new theory of temperature, right, then, maybe we could check that it says that boiling water is hotter than ice. And then if it says that the sun is hotter than anything, you've ever experienced, then maybe we trust that extrapolation, right? But like this theory, like if it's now saying that, a gigantic grid, like regular grid of exclusive OR gates, can be way more conscious than a person or than any animal can be, even if it, is so uniform that it might as just be a blank wall, right? And so now the point is, if this theory is sort of getting wrong the question, is a blank wall, more conscious than a person, then I would say, what is there for it to get right?
So
right?
your sense is a blank wall is not more conscious than a human being.
Yeah, I mean, you could say that I am taking that as one of my axioms. I'm saying that if a theory of consciousness is getting that wrong, then whatever it is talking about at that point, I'm not going to call it consciousness. Well, I'm going to use a different word.
You have to use a different word.
Yeah,
I mean, it's possible, just like with intelligence, that us humans conveniently define these very difficult to understand concepts in a very human-centric way. Just like the Turing test really seems to define intelligence as a thing that's human-like.
Right, but I would say that with any concept, there's like we first need to define it, right? And a definition is only a good definition if it matches what we thought we were talking about, prior to having a definition, right?
Yeah.
And I would say that, phi as a definition of consciousness fails that test. That is my argument.
So, okay, then let's take a further step. So you mentioned that the universe might be the Turing machine. So like it might be computation.
Or simulatable by one anyway.
Simulatable by one. What's your sense about consciousness? Do you think consciousness is computation, that we don't need to go to any place outside of the computable universe to understand consciousness, to build consciousness, to measure consciousness, all those kinds of things?
I don't know. These are what have been called the vertiginous questions, right? They're
What's
the
that?
questions that you get a feeling of vertigo when thinking about them, right? I mean, I certainly feel like I am conscious in a way that is not reducible to computation, but why should you believe me?
Yeah.
Right? I mean, and if you said the same to me, then why should I believe you?
But as computer
Yeah.
scientists, I feel like a computer could achieve human level intelligence, but and that's actually a feeling and a hope. That's not a scientific
Hmm.
belief.
Hmm.
It's just we've built up enough intuition, the same kind of intuition you use in your blog. It's, that's what scientists do. I mean, some of
Hmm.
it is a scientific method, but some of it is just damn good
Hmm.
intuition.
Hmm.
I don't have a good intuition about consciousness.
Yeah. I'm not sure that anyone does or has in the, 2,500 years that these things have been discussed, Lex.
But do you think we will? Like
Well,
I got a chance to
mhm,
attend. Can't wait to hear your opinion on this. But attend the Neuralink event, and one of the dreams there is to, basically push neuroscience forward. And the
mhm,
hope with neuroscience is that we can inspect the machinery from which all this fun stuff emerges and see, are we going to notice something special, some special sauce from which something like consciousness or cognition emerges?
yeah, well, it's clear that we've learned an enormous amount about neuroscience. We've learned an enormous amount about computation, about
All right.
machine learning, about
Neural networks.
AI, how to get it to work. We've learned an enormous amount about the underpinnings of the physical world, and from one point of view, that's like an enormous distance that we've traveled along the road to understanding consciousness. From another point of view, the distance still to be traveled on the road, maybe seems no shorter than it was at the beginning,
Yeah.
right? So it's very hard to say. I mean, these are questions like in sort of trying to have a theory of consciousness. There's sort of a problem where it feels like it's not just that we don't know how to make progress, it's that it's hard to specify what could even count as progress, right?
Right.
Because no matter what scientific theory someone proposed, someone else could come along and say, well, you've just talked about the mechanism. You haven't said anything about what breathes fire into the mechanism, what
Right.
really makes there something that it's like to be it, right? And that seems like an objection that you could always raise,
Yes.
no matter how much someone elucidated the details of how the brain works.
Okay, let's go Turing test and Loebner prize. I have this intuition, call me crazy, but that a machine to pass the Turing test in its full, whatever the spirit of it is, we can talk about how to formulate the perfect Turing test, that machine has to be conscious, or we at least have to. I have a very low bar of what consciousness is. I tend to think that the emulation of consciousness is as good as consciousness.
Mm.
So like consciousness is just a dance, a social shortcut, like a nice useful tool. But I tend to connect intelligence and consciousness together. So by that, do you maybe just to ask what role does consciousness play? Do you think in passing the Turing test?
Well, look, I mean, it's almost tautologically true that if we had a machine that passed the Turing test, then it would be emulating consciousness, right? So if your position is that, emulation of consciousness is consciousness, then, by definition, any machine that passed the Turing test would be conscious.
But
Right.
it's
But I mean, that you could say that, that is just a way to rephrase the original question, is an emulation of consciousness, necessarily conscious, right? And you I'm not saying anything new that hasn't been debated ad nauseum in the literature. Okay. But, you could imagine some very hard cases, like imagine a machine that passed the Turing test, but that did so just by an enormous cosmological sized lookup table,
Yeah.
that just cached every possible conversation that could be had.
The old
And then
Chinese room
well,
argument.
yeah, but this is, I mean, the Chinese room actually would be doing some computation, at least in Searle's version,
Yeah.
right? Here, I'm just talking about a table lookup. Okay, now it's true that for conversations of a reasonable length, this lookup table would be so enormous it wouldn't even fit in the observable universe. Okay, but supposing that you could build a big enough lookup table and then just pass the Turing test just by looking up what the person said, right? Are you going to regard that as conscious?
Okay, let me try to make this
Yeah.
formal, and then you can
Okay.
shut it down.
All right.
I think that the emulation of something is that something if there exists in that system a black box that's full of mystery. So like
Okay. Full of mystery to whom? By the
to human inspectors.
So does that mean that consciousness is relative to the observer? Like, could something be conscious for us, but not conscious for an alien that understood better what was
Right.
happening inside the black box?
Yes. So that if inside the black box is just a lookup table, the alien that saw that would say this is not conscious. To us, another way to phrase the black box, there's layers of abstraction which make it very difficult to see to the actually underlying functionality of the system. And then we observe just the abstraction, and so it looks like magic to us. But once we understand the inner machinery, it stops being magic. And so like that's a prerequisite, is that you can't know how it works, some part of it, because then there has to be in our human mind entry point for the magic. So that's a formal definition of the system.
Yeah, well, look, I mean, I explored a view in this essay I wrote called "The Ghost and the Quantum Turing Machine" 7 years ago that is related to that, except that I did not want to have consciousness be relative to the observer, right? Because I think that, if consciousness means anything, it is something that is experienced by the entity that is conscious, right? Like I don't need you to tell me that I'm conscious, right? Nor do you need me to tell you that you are, right? But basically what I explored there is, are there aspects of a system like a brain that just could not be predicted, even with arbitrarily advanced future technologies.
Yeah.
It's because of chaos combined with quantum mechanical uncertainty, and things like that. I mean, that actually could be a property of the brain, if true, that would distinguish it in a principled way, at least from any currently existing computer. Not from any possible computer, but from
Let's do a thought experiment. So if I gave you information that the entire history of your life, basically explain away free will with a lookup table. Say that this was all predetermined, that everything you experience has already been predetermined. Wouldn't that take away your consciousness? Wouldn't you yourself, the experience of the world change for you in a way that's you can't take back?
Let me put it this way. If you could do like in a Greek tragedy where, you would just write down a prediction for what I'm going to do, and then maybe you put the prediction in a sealed box, and maybe, you open it later and you show that you knew everything I was going to do. Or, of course, the even creepier version would be you tell me the prediction and then I try to falsify it, and my very effort to falsify it makes it come true. Right.
Oh,
Let's even forget that, that version, as convenient as it is for fiction writers. Right.
Yeah.
And let's just do the version where you put the prediction into a sealed envelope. Okay. But if you could reliably predict everything that I was going to do, I'm not sure that would destroy my sense of being conscious, but I think it really would destroy my sense of having free will, and much, much more than any philosophical conversation could possibly do that. Right.
Yeah.
And so I think it becomes extremely interesting to ask, could such predictions be done, even in principle? Is it consistent with the laws of physics to make such predictions, to get enough data about someone that you could actually generate such predictions without having to kill them in the process, to, slice their brain up into little slivers or something?
I mean, it's theoretically possible, right?
Well, I don't know. I mean, it might be possible, but only at the cost of destroying the person. right? I mean, it depends on how low you have to go in sort of the substrate. Like if there was a nice digital abstraction layer, if you could think of each neuron as a kind of transistor computing a digital function, then you could imagine some nanorobots that would go in and would just scan the state of each transistor, of each neuron, and then, make a good enough copy, right? But if it was actually important to get down to the molecular or the atomic level, then, eventually you would be up against quantum effects. You would be up against the unclonability of quantum states. So I think it's a question of how good does the replica have to be before you're going to count it as actually a copy of you or as being able to predict your actions.
And that's a totally open question.
Yeah, and especially once we say that, well, look, maybe there's no way to to make a deterministic prediction because we know that there's noise buffeting the brain around, presumably even quantum mechanical uncertainty, affecting the sodium ion channels, for example, whether they open or they close. There's no reason why over a certain time scale that shouldn't be amplified, just like we imagine happens with the weather or with any other, chaotic system. So if that stuff is important, right, then we would say, well, you can't, you're never going to be able to make an accurate enough copy. But now the hard part is, well, what if someone can make a copy that sort of no one else can tell apart from you, right? It says the same kinds of things that you would have said, maybe not exactly the same things because we agree that there's noise, but it says the same kinds of things. And maybe you alone would say, no, I know that that's not me. It doesn't share I haven't felt my consciousness leap over to that other thing. I still feel it localized in this version, right? And then why should anyone else believe you?
What are your thoughts? I'd be curious. You're a really good person to ask, which is Roger Penrose's work on consciousness, saying that there is some, with axons and so on, there might be some biological places where quantum mechanics can come into play and through that create consciousness somehow.
Yeah. Okay. Well,
familiar with his work at all?
Of course. I read Penrose's books as a teenager. They had a huge impact on me. 5 or 6 years ago, I had the privilege to actually talk these things over with Penrose, at some length at a conference in Minnesota. And, he is, an amazing personality. I admire the fact that he was even raising such audacious questions at all. But, to answer your question, I think the first thing we need to get clear on is that he is not merely saying that quantum mechanics is relevant to consciousness, right? That would be like, that would be tame compared to what he is saying, right? He is saying that, even quantum mechanics is not good enough, right? Because if supposing, for example, that the brain were a quantum computer, right, that's still a computer. Yeah. In fact, a quantum computer can be simulated by an ordinary computer. Right. It might merely need exponentially more time in order to do so, right? So that's simply not good enough for him. Okay, so what he wants is for the brain to be a quantum gravitational computer. Or he wants the brain to be exploiting as yet unknown laws of quantum gravity. Okay, which would be uncomputable.
Uncomputable. That's the key point.
Okay, yes. That would be literally uncomputable. And I've asked him, to clarify this, but uncomputable, even if you had an oracle for the halting problem, or as high up as you want to go in the sort of the usual hierarchy of uncomputability. He wants to go beyond all of that. Okay, so just to be clear, like, if we're keeping count of how many speculations, there's probably like at least 5 or 6 of them, right? There's, first of all, that there is some quantum gravity theory that would involve this kind of uncomputability, right? Most people who study quantum gravity would not agree with that. They would say that what we've learned, what little we know about quantum gravity from this ADS-CFT correspondence, for example, has been very much consistent with the broad idea of nature being computable, right? But all right, but supposing that he's right about that, then what most physicists would say is that whatever new phenomena there are in quantum gravity, they might be relevant at the singularities of black holes. They might be relevant at the Big Bang. They are plainly not relevant to something like the brain, that is operating at ordinary temperatures, right, with ordinary chemistry, and the physics underlying the brain. They would say that we have, the fundamental physics of the brain. They would say that we've pretty much completely known for generations now, right? Because quantum field theory lets us sort of parameterize our ignorance, right? I mean, Sean Carroll has made this case, and in great detail, right? That sort of whatever new effects are coming from quantum gravity, they are sort of screened off by quantum field theory, right? And this brings us to the whole idea of effective theories, right? But that, like, we have, in the standard model of elementary particles, right? We have a quantum field theory that seems totally adequate for all of the terrestrial phenomena, right? The only things that it doesn't, explain are, well, first of all, the details of gravity. If you were to probe it, like at extremes of, curvature, or at like incredibly small distances, it doesn't explain dark matter. It doesn't explain black hole singularities, right? But these are all very exotic things, very, far removed from our life on Earth. Yeah. Right. So for Penrose to be right, he needs, these phenomena to somehow affect the brain. He needs the brain to contain antennae that are sensitive to this
black holes,
to this as yet unknown physics. Right. Yeah. And then he needs a modification of quantum mechanics. Okay. So he needs quantum mechanics to actually be wrong. Okay, he needs what he wants is what he calls an objective reduction mechanism, or an objective collapse. So this is the idea that once quantum states get large enough, then they somehow spontaneously collapse, right? That and this is an idea that lots of people have explored. There's something called the GRW proposal that tries to, say something along those lines. And these are theories that actually make testable predictions, right? Which is a nice feature that they have. Mm-hmm. But the very fact that they're testable may mean that in the in the coming decades, we may well be able to test these theories and show that they're wrong. Right. We may be able to test some of Penrose's ideas, if not his ideas about consciousness, but at least his ideas about an objective collapse of quantum states. Right. And people have actually, like Dick Baumeister, have actually been working to try to do these experiments. They haven't been able to do it yet, to test Penrose's proposal. Okay. But Penrose would need more than just an objective collapse of quantum states, which would already be the biggest development in physics for a century, since quantum mechanics itself. Okay. He would need, for consciousness to somehow be able to influence the direction of the collapse, so that it wouldn't be completely random, but that, your dispositions would somehow influence the quantum state to collapse more likely this way or that way. Okay. Yep. Finally, Penrose, says that all of this has to be true because of an argument that he makes based on Gödel's incompleteness theorem. Okay. Right. Now, like I would say the overwhelming majority of computer scientists and mathematicians who have thought about this, I don't think that Gödel's incompleteness theorem can do what he needs it to do here, right? I don't think that argument is sound. Okay. But that is sort of the tower that you have to ascend to if you're going to go where Penrose goes.
And the intuition he uses with the incompleteness theorem is that basically that there's important stuff that's not computable.
No, it's not. It's not just that, because everyone agrees that there are problems that are uncomputable, right? That's a mathematical theorem, right? But what Penrose wants to say is that for example, there are statements, given any formal system, for doing math, right? There will be true statements of arithmetic that formal system, if it's adequate for math at all, if it's consistent and so on, will not be able to prove. A famous example being the statement that system itself is consistent, right? Right. No, good formal system can actually prove its own consistency. consistency that can only be done from a stronger formal system, which then can't prove its own consistency, and so on forever. Okay, that's Gödel's theorem. But now, why is that relevant to consciousness, right? Well, the idea that it might have something to do with consciousness is an old one. Gödel himself apparently thought that it did.
Oh, really? That's interesting.
Lucas thought so, I think, in the 60s. And Penrose is really just, sort of updating what they and others had said. I mean, the idea that Gödel's theorem could have something to do with consciousness was, in 1950, when Alan Turing wrote his article about the Turing test. He already, was writing about that as like an old and well-known idea, and as one that as a wrong one that he wanted to dispense with. Right.
Yeah.
Okay. But the basic problem with this idea is, Penrose wants to say that, and all of his predecessors here, want to say that, even though, this given formal system cannot prove its own consistency, we as humans, sort of looking at it from the outside, can just somehow see its consistency. Right. And the rejoinder to that, from the very beginning has been, well, can we really?
Yeah.
I mean, maybe, Penrose can, but, can the rest of us?
Yeah.
Right. And, I noticed that, it is perfectly plausible to imagine a computer that could say, it would not be limited to working within a single formal system, right? They could say, I am now going to adopt the hypothesis that my formal system is consistent, right? And I'm now going to see what can be done from that stronger vantage point, and so on. And, and I'm going to add new axioms to my system. Totally plausible. There's absolutely, Gödel's theorem has nothing to say against an AI that could repeatedly add new axioms. All it says is that there is no absolute guarantee that when the AI adds new axioms that it will always be right.
Right.
Okay. And, and that's, of course, the point that Penrose pounces on. But the reply is obvious. And, it's one that Alan Turing made 70 years ago. Namely, we don't have an absolute guarantee that we're right when we add a new axiom.
Right.
We never have, and plausibly we never will.
So on Alan Turing, you took part in the Loebner Prize?
Not really. No, I didn't. I mean, there was this kind of ridiculous claim that was made almost a decade ago about a chat bot called Eugene Goostman.
Yeah, I apologize. I guess you didn't participate as a judge in the Loebner Prize.
I didn't, no.
But you participated as a judge in that. I guess it was an exhibition event or something like that. Or with Eugene...
Eugene Goostman, that was just me writing a blog post because some journalists called me to ask about it.
Did you ever chat with him?
I did chat with Eugene Goostman. Okay. I mean, it was available on the web to chat.
Oh, interesting. I didn't know.
So, yeah. So all that happened was that, a bunch of journalists started writing breathless articles about, first chatbot that passes the Turing test, right? And it was this thing called Eugene Goostman that was supposed to simulate a 13-year-old boy.
Yeah.
And, and apparently someone had done some test where, people couldn't, were less than perfect, let's say, distinguishing it from a human. And they said, well, if you look at Turing's paper and you look at, the percentages that he talked about, then, it seems like we're past that threshold. Right. And, I had a sort of, different way to look at it instead of the legalistic way. Like, let's just try the actual thing out and let's see what it can do with questions like, is Mount Everest bigger than a shoebox? Right. Okay. Or just, like the most obvious questions. Right. And the answer is, well, it just kind of parries you because it doesn't know what you're talking about. Right.
So just to clarify exactly in which way they're obvious. They're obvious in the sense that you convert the sentences into the meaning of the objects they represent and then do some basic obvious, your common sense reasoning with the objects that the sentences represent.
Right. It was not able to answer, or even intelligently respond to basic common sense questions. But let me say something stronger than that. There was a famous chatbot in the 60s called Eliza, right? That, that managed to actually fool, a lot of people, right? Or people would pour their hearts out into this ELIZA because it simulated a therapist, right? And most of what it would do is it would just throw back at you whatever you said, right? And this turned out to be incredibly effective, right? Maybe therapists know this. This is one of their tricks, but it it really had some people convinced. But this thing was just like, I think it was literally just a few hundred lines of Lisp code, right? It was not only was it not intelligent, it wasn't especially sophisticated.
Yeah.
It was a simple little hobbyist program. And Eugene Goostman, from what I could see, was not a significant advance compared to ELIZA. Right. And that was really the point I was making. And this was, you didn't, in some sense, you didn't need a computer science professor to sort of say this. Like, anyone who was looking at it and who just had, an ounce of sense could have said the same thing. Right.
Well,
but because, these journalists were calling me, like the first thing I said was, well, no, I'm a quantum computing person. I'm not an AI person. You shouldn't ask me. But then they said, look, you can go here and you can try it out. I said, all right. So I'll try it out. But now, this whole discussion, I mean, it got a whole lot more interesting in just the last few months.
Yeah, I'd love to hear your thoughts about GPT-3.
In the last few months, we've had, the world has now seen a chat engine, or a text engine, I should say, called GPT-3. That, I think it still, it does not pass a Turing test. There are no real claims that it passes the Turing test, right? This comes out of the group at OpenAI, and, they've been relatively careful in what they've claimed about the system. But I think this as clearly as Eugene Goostman was not an advance over ELIZA, it is equally clear that this is a major advance over ELIZA, or really over anything that the world has seen before. This is a text engine that can come up with kind of on-topic, reasonable sounding completions to just about anything that you ask. You can ask it to write a poem about topic X in the style of poet Y, and it will have a go at that.
Yeah.
And it will do, not a great job, not an amazing job, but, a passable job, definitely, as good as, in many cases, I would say better than I would have done, right? You can ask it to write, an essay, like a student essay about pretty much any topic, and it will get something that I am pretty sure would get at least a B-, in most, high school or even college classes, right? And, in some sense, the way that it did this, the way that it achieves this, Scott Alexander of the much mourned blog, Slate Star Codex, had a wonderful way of putting it. He said that they basically just ground up the entire internet into a slurry. Okay.
Yeah.
And, and I, to tell you the truth, I had wondered for a while why nobody had tried that, right? Like, why not write a chatbot by just doing deep learning over a corpus consisting of the entire web, right? And so now they finally have done that, right? And, the results are very impressive. It's not clear that, people can argue about whether this is truly a step toward general AI or not. But this is an amazing capability that, we didn't have a few years ago. That, if a few years ago, if you had told me that we would have it now, that would have surprised me.
Yeah.
And I think that anyone who denies that is just not engaging with what's there.
So their model, it takes a large part of the internet and compresses it in a small number of parameters relative to the size of the internet, and is able to, without fine-tuning, do a basic kind of a querying mechanism, just like you described, where you specify a kind of poet and then that you want to write a poem, and it somehow is able to do basically a lookup on the internet
Well,
of relevant things. I mean, that's what it, how else do you explain it?
Well, okay. The training involved, massive amounts of data from the internet, and actually took lots and lots of computer power, lots of electricity, right? There are some very prosaic reasons why this wasn't done earlier, right?
Right.
But it costs some tens of millions of dollars, I think.
Less,
just
but,
for
approximately like a few $1,000,000.
Oh, okay. Oh, really? Okay.
It's more like 4 or 5.
Oh, all right. Thank you. I mean, as they scale it up, it will.
It'll cost, but then the hope is cost comes down, all that kind of stuff.
But basically, it is a neural net, so or what's now called a deep net, but they're basically the same thing, right? So it's a form of algorithm that people have known about for decades, right? But it is constantly trying to solve the problem, predict the next word, right? So it's just trying to predict what comes next. It's not trying to decide what it should say, what ought to be true. It's trying to predict what someone who had said all of the words up to the preceding one would say next.
Although to push back on that, that's how it's trained. But
that's right. No,
but it's arguable
yeah.
that our very cognition could be a mechanism as that simple.
Of course. I never said that it wasn't.
Right. But
yeah.
But
in some sense that is, if there is a deep philosophical question that's raised by GPT-3, then that is it. Right? Are we doing anything other than, this predictive processing, just constantly trying to fill in a blank of what would come next after what we just said up to this point? Is that what I'm doing right now?
Is it possible? So the intuition that a lot of people have, well, look, this thing is not going to be able to reason. The Mountain Everest question. Do you think it's possible that GPT 5, 6, and 7 would be able to, with this exact same process, begin to do something that looks like is indistinguishable to us humans from reasoning?
The truth is that we don't really know what the limits are, right?
Exactly.
Because what we've seen so far is that, GPT-3 was basically the same thing as GPT-2, but just with, a much larger network, more training time, bigger training corpus, right? And it was, very noticeably better, right, than its immediate predecessor. So we don't know where you hit the ceiling here, right? That's the amazing part, and maybe also the scary part, right? That now my guess would be that at some point, like, there has to be diminishing returns. Like, it can't be that simple, can it? Right.
Well,
but I wish that I had more to base that guess on.
Right. Yeah. Some people say that there will be a limitation on we're going to hit a limit on the amount of data that's on the internet.
Yes. Yeah. So sure. So there's certainly that limit. There's also, like if you are looking for questions that will stump GPT-3, right, you can come up with some without, even getting it to learn how to balance parentheses, right? Like it can, it doesn't do such a great job, right? And its failures are ironic, right? Like basic arithmetic, right? And you think, isn't that what computers are supposed to be best at?
Yeah.
Isn't that where computers already had us beat a century ago?
Yeah.
Right. And yet that's where GPT-3 struggles, right?
Yeah.
But it's amazing, that it's almost like a young child in that way, right? That somehow, because it is just trying to predict what comes next, it doesn't know when it should stop doing that and start doing something very different, like some more exact logical reasoning, right? And so one is naturally led to guess that our brain sort of has some element of predictive processing, but that it's coupled to other mechanisms, right? That it's coupled to, first of all, visual reasoning, which GPT-3 also doesn't have any of, right?
Although there's some demonstration that there's a lot of promise there.
It can complete images. That's right.
Yeah, and using exact same kind of transformer mechanisms to like watch videos on YouTube and so the same self-supervised mechanism to be able to learn. It'd be fascinating to think what kind of completions you could do.
Oh yeah, no, absolutely. Although, like, if we ask it to, like, a word problem that involves reasoning about the locations of things in space, I don't think it does such a great job on those, right? To
Right.
take an example, and so the guess would be, well, humans have a lot of predictive processing, a lot of just filling in the blanks, but we also have these other mechanisms that we can couple to, or that we can sort of call as subroutines when we need to, and that maybe to go further, that one would want to integrate other forms of reasoning.
Let me go on another
Yeah,
topic
sure.
that is amazing, which is complexity.
Hmm.
What and then start with the most absurdly romantic question of what's the most beautiful idea in computer science or theoretical computer science to you? Like what just
Yeah.
early on in your life or in general have
Yeah.
captivated you and just grabbed you?
I think I'm going to have to go with the idea of universality. Uh, if you're really asking for the most beautiful, I mean, so universality is the idea that, you put together a few simple operations, like, in the case of Boolean logic, that might be the AND gate, the OR gate, the NOT gate, right? And then your first guess is, okay, this is a good start. But obviously, as I want to do more complicated things, I'm going to need more complicated building blocks to express that, right? And that was actually my guess when I first learned what programming was. I mean, when I was, an adolescent, and someone showed me Apple Basic, and then GW Basic. If
Oh wow.
anyone listening remembers that, okay. But I thought, okay, well now, I felt like this is a revelation. It's like finding out where babies come from. It's like that level of, why didn't anyone tell me this
Yeah.
before, right? But I thought, okay, this is just the beginning. Now I know how to write a basic program, but to, really write an interesting program, like a video game, which had always been my dream as a kid, to, create my own Nintendo games, right? That, but obviously I'm going to need to learn some way more complicated form of programming than that. Okay. But eventually I learned this incredible idea of universality. And that says that no, you throw in a few rules and then you already have enough to express everything. Okay, so for example, the and, the or, and the not gate can all, or in fact, even just the and the not gate, or
Right. Exactly.
even just the NAND gate, for example, is already enough to express any Boolean function on any number of bits. You just have to string together enough of them.
You can
Right?
build a universe with NAND gates.
You can build the universe out of NAND gates. Yeah. The simple instructions of BASIC are already enough, at least in principle. If we ignore details like how much memory can be accessed and stuff like that, that is enough to express what could be expressed by any programming language whatsoever. And the way to prove that is very simple. We simply need to show that in BASIC or whatever, we could write an interpreter or a compiler for whatever is other programming language we care about, like C or Java or whatever. And as soon as we had done that, then ipso facto, anything that's expressible in C or Java is also expressible in BASIC. Okay, and so this idea of universality, goes back at least to Alan Turing in the 1930s, when he wrote down this incredibly simple pared down model of a computer, the Turing machine, right? Which he pared down the instruction set to just read a symbol, write a symbol, move to the left, move to the right, halt, change your internal state. Right, that's it.
Simple.
Okay, but he proved that this could simulate all kinds of other things. And so in fact today we would say, well, we would call it a Turing universal model of computation that is, it has just the same expressive power that BASIC or Java or C++ or any of those other languages have, because anything in those other languages could be compiled down to Turing machine. Now, Turing also proved a different related thing, which is that there is a single Turing machine that can simulate any other Turing machine if you just describe that other machine on its tape. right? And likewise, there is a single Turing machine that will run any C program, if you just put it on its tape. That's a second meaning of universality.
Mm-hmm. First of all, that he couldn't visualize it, and that was in the 30s, I think.
The 30s. That's right.
Before computers really. I mean, I don't know how. I wonder what that felt like.
Yeah.
Learning that there's no Santa Claus or something. Because I don't know if that's empowering or paralyzing. Because it doesn't give you any. It's like you can't write a software engineering book and make that the first chapter and say we're done.
Well, I mean, right. In one sense, it was this enormous flattening of the universe.
Yes.
Right. Like I had imagined that there was going to be some infinite hierarchy of more and more powerful programming languages. And then I kicked myself for having such a stupid idea. But apparently Gödel had the same conjecture in the 30s.
Oh, good.
And then
you're in good company.
And then Gödel read Turing's paper and he kicked himself and he said, "Yeah, I was completely wrong about that." Okay, but I had thought that maybe where I can contribute will be to invent a new, more powerful programming language that lets you express things that could never be expressed in BASIC.
Yeah.
Right. And how would you do that? Obviously, you couldn't do it itself in BASIC, right? But there is this incredible flattening that happens once you learn what is universality. But then it's also an opportunity, because it means once you know these rules, then the sky is the limit, right? Then you have kind of the same weapons at your disposal that the world's greatest programmer has. It's now all just a question of how you wield them.
Right, exactly. Right? But so every problem is solvable, but some problems are harder than others. And
there's the question of how much time, of how hard is it to write a program, and then there's also the questions of what resources does the program need? How much time, how much memory? Those are much more complicated questions, of course, ones that we're still struggling with today.
Exactly. So you've I don't know if you created Complexity Zoo or
I did create the Complexity Zoo.
What is it? What's complexity?
Oh, all right. Complexity theory is the study of sort of the inherent resources needed to solve computational problems. Mm-hmm. Okay, so it's easiest to give an example. Let's say we want to add two numbers, right? If I want to add them, if the numbers are twice as long, then it will take me twice as long to add them, but only twice as long, right? It's no worse than that.
For a computer.
For a computer or for a person, we're using pencil and paper for that matter.
If you have a good algorithm.
Yeah, that's right. Even if you just use the elementary school algorithm of just carrying, then it takes time that is linear in the length of the numbers, right? Now, multiplication, if you use the elementary school algorithm, is harder because you have to multiply each digit of the first number by each digit of the second one.
Yeah.
And then deal with all the carries. So that's what we call a quadratic time algorithm. Right. If the numbers become twice as long, now you need 4 times as much time. Okay. So now, as it turns out, people discovered much faster ways to multiply numbers using computers. Mm-hmm. And today we know how to multiply 2 numbers that are n digits long using a number of steps that's nearly linear in n. These are questions you can ask, but now let's think about a different thing that people, they've encountered in elementary school, factoring a number. Mm-hmm. Okay, take a number and find its prime factors, right? And here, if I give you a number with 10 digits, I ask you for its prime factors. Well, maybe it's even, so you know that 2 is a factor. Maybe it ends in 0, so you know that 10 is a factor, right? But, other than a few obvious things like that, if the prime factors are all very large, then it's not clear how you even get started, right? It seems like you have to do an exhaustive search among an enormous number of factors. Now, as many people might know, for better or worse, the security, of most of the encryption that we currently use to protect the internet is based on the belief, and this is not a theorem, it's a belief that that factoring is an inherently hard problem. for our computers. We do know algorithms that are better than just trial division and just trying all the possible divisors, but they are still basically exponential.
And
Okay?
exponential is hard.
Yeah, exactly. So the fastest algorithms that anyone has discovered, at least publicly discovered, I'm assuming that the NSA doesn't know something better.
Yeah.
Okay, but they take time that basically grows exponentially with the cube root of the size of the number that you're factoring, right? So that cube root, that's the part that takes all the cleverness. Okay, but there's still an exponential. There's still an exponentiality there. But what that means is that, like, when people use 1,000-bit keys for their cryptography, that can probably be broken using the resources of the NSA or the world's other intelligence agencies. People have done analyses that say, with a few $100 million of computer power, they could totally do this. And if you look at the documents that Snowden released, it looks a lot like they are doing that or something like that. It would kind of be surprising if they weren't. Okay, but if that's true, then in some ways that's reassuring, because if that's the best that they can do, then that would say that they can't break 2,000-bit numbers.
Right. Exactly.
Right. Then 2,000-bit numbers would be beyond what even they could do.
They haven't found an efficient algorithm. That's where all the worries and the concerns of quantum computing came in. That there could be some kind of shortcut around that.
Right. So complexity theory is a huge part of, let's say, the theoretical core of computer science. It started in the 60s and 70s as sort of an autonomous field. So it was already it was well developed even by the time that I was born. Okay, but in 2002 I made a website called the Complexity Zoo to answer your question, where I just tried to catalog the different complexity classes, which are classes of problems that are solvable with different kinds of resources. Right. Okay, so these are kind of you could think of complexity classes as like being almost to theoretical computer science like what the elements are to chemistry, right? They're sort of there are our most basic objects in a certain way.
I feel like the elements have a characteristic to them where you can't just add an infinite number.
Well, you could, but beyond a certain point, they become unstable. Okay. Right. So it's like, in theory, you can have atoms with, and look, I mean, a neutron star, is a nucleus with, untold billions of neutrons in it, of hadrons in it. Okay. But, for sort of normal atoms, right, probably you can't get much above 100, atomic weight, 150 or so. Or sorry, I mean, beyond 150 or so protons without it, very quickly fissioning. With complexity classes, well, yeah, you can have an infinity of complexity classes, but maybe there's only a finite number of them that are particularly interesting, right? Just like with anything else, you care about some more than about others.
So, what kind of interesting classes are there?
Yeah,
I mean, you could have just maybe say what are if you take any kind of computer science class, what are the classes you learn?
Good. Let me tell you sort of the biggest ones, the ones that you would learn first. So, first of all, there is P. That's what it's called. Okay, it stands for polynomial time. And this is just the class of all of the problems that you could solve with a conventional computer, like your iPhone or your laptop, by a completely deterministic algorithm, right? Using a number of steps that grows only like the size of the input raised to some fixed power. Mm-hmm. Okay. So if your algorithm is linear time, like, for adding numbers, okay, that problem is in P. If you have an algorithm that's quadratic time, like the elementary school algorithm for multiplying two numbers, that's also in P. Even if it was the size of the input to the 10th power or to the 50th power, well, that wouldn't be very good in practice. But, formally, we would still count that. That would still be in P. Okay, but if your algorithm takes exponential time, meaning like if every time I add one more data point to your input, if the time that needed by the algorithm doubles, if you need time like 2 to the power of the amount of input data, then that we call an exponential time algorithm. Okay, and that is not polynomial. Okay, so P is all of the problems that have some polynomial time algorithm. Okay, so that includes most of what we do with our computers on a day-to-day basis. All the sorting, basic arithmetic, whatever is going on in your email reader or in Angry Birds. Okay, it's all in P.
Got it.
Then the next super important class is called NP. That stands for non-deterministic polynomial. Okay, does not stand for not polynomial, which is a common confusion. But NP is basically all of the problems where if there is a solution, then it is easy to check the solution if someone shows it to you. Okay, so actually a perfect example of a problem in NP is factoring. The one I told you about before. Like if I gave you a number with thousands of digits and I told you that I asked you, does this have at least 3 non-trivial divisors? Right? That might be a super hard problem to solve, right? It might take you millions of years using any algorithm that's known, at least running on our existing computers. Okay, but if I simply showed you the divisors, I said, here are 3 divisors of this number, then it would be very easy for you to ask your computer to just check each one and see if it works. Just divide it in, see if there's any remainder, right? And if they all go in, then you've checked. Well, I guess there were, right? So, so any problem where, wherever there's a solution, there is a short witness that can be easily, like a polynomial size witness that can be checked in polynomial time. That we call an NP problem. Okay.
Beautiful.
And so every problem that's in P is also in NP, right? Because, you could always just ignore the witness and just, if a problem is in P, you can just solve it yourself.
Right.
Okay. But now in some sense, the central, mystery of theoretical computer science is every NP problem in P. So if you can easily check the answer to a computational problem, does that mean that you can also easily find the answer?
Even though there's all these problems that appear to be very difficult to find the answer, it's still an open question whether a good answer exists. So
because no one has proven that there's no way to do it.
It's
right?
arguably the most I don't know, the most famous, the most maybe interesting, maybe you disagree with that, problem in theoretical computer science. So what's your...
The most famous, for sure.
P equals NP.
Yeah.
If you were to bet all your money, where do you put your money?
That's an easy one. P is not equal to NP.
Okay, so...
I like to say that if we were physicists, we would have just declared that to be a law of nature. Just like thermodynamics.
That's hilarious.
Just giving ourselves Nobel Prizes for its discovery.
Funny.
Yeah, no. And look, if later it turned out that we were wrong, we just give ourselves more Nobel Prizes. Yeah. I mean, because we're
so harsh but so true.
It's really just because we are mathematicians or descended from mathematicians. We have to call things conjectures that other people would just call empirical facts or discoveries, right?
Okay,
but one shouldn't read more into that difference in language, about the underlying truth.
So you're a good investor and good spender of money. So then let me ask another way. Is it possible at all? And what would that look like if P indeed equals NP?
Mm-hmm. Well, I do think that it's possible. I mean, in fact, when people really pressed me on my blog for what odds would I put 2 or 3% odds.
That's pretty good.
That P equals NP. Yeah, because when P, you really have to think about, like, if there were 50 mysteries like P versus NP, and if I made a guess about every single one of them, would I expect to be right 50 times? Right, and the truthful answer is no. Okay.
Yeah.
So and that's what you really mean in saying that you have better than 98% odds for something. Okay. But, there could certainly be surprises. And look, if P equals NP, well, then there would be the further question of, is the algorithm actually efficient in practice? Right. I mean, Don Knuth, who I know that you've interviewed as well, right? Yeah. He likes to conjecture that P equals NP, but that the algorithm is so inefficient that it doesn't matter anyway. right? Now, I don't know. I've listened to him say that. I don't know whether he says that just because he has an actual reason for thinking it's true or just because it sounds cool.
Yeah.
Okay. But you know, that's a logical possibility, right? That the algorithm could be n to the 10,000 time, or it could even just be n squared time, but with a leading constant of it could be a Google times n squared or something like that. And in that case, the fact that p equals np, well, it would ravage the whole theory of complexity. We would have to, rebuild from the ground up. But in practical terms, it might mean very little, right? If the algorithm was too inefficient to run. If the algorithm could actually be run in practice, like if it had small enough constants, or if you could improve it to where it had small enough constants that it was efficient in practice, then that would change the world. Okay.
You think it would have, like, what kind of impact would it have?
Okay. I mean, here's an example. I mean, just for starters, you could break basically all of the encryption that people use to protect the internet.
For starters.
You could break Bitcoin and every other cryptocurrency, or mine as much Bitcoin as you wanted, right? Become a super duper billionaire, right? And then plot your next move,
Right.
Okay,
That's just for starters.
Right. Now your next move might be something like, you now have like a theoretically optimal way to train any neural network, to find parameters for any neural network, right?
Yeah.
So you could now say, like, is there any small neural network that generates the entire content of Wikipedia, right? And now the question is not, can you find it? The question has been reduced to, does that exist or not?
Yes.
If it does exist, then the answer would be yes, you can find it. Okay, if you had this algorithm in your hands, okay, you could ask your computer. P versus NP is one of these 7 problems that carries this $1 million prize from the Clay Foundation. If you solve it, and others are the Riemann hypothesis, the Poincare conjecture, which was solved, although the solver turned down the prize, right? And 4 others. But what I like to say, the way that we can see that P versus NP is the biggest of all of these questions is that if you had this fast algorithm, then you could solve all 7 of them. Okay, you just ask your computer, is there a short proof of the Riemann hypothesis, right? That a machine could, in a language where a machine could verify it, and provided that such a proof exists, then your computer finds it in a short amount of time without having to do a brute force search. Okay, so those are the stakes of what we're talking about. But I hope that also helps to give your listeners some intuition of why I and most of my colleagues would put our money on P not equaling NP.
Is it possible, I apologize, this is a really dumb question, but is it possible that a proof will come out that P equals NP, but an algorithm that makes P equals NP is impossible to find? Is that like crazy?
Okay, well, if P equals NP, it would mean that there is such an algorithm. Right?
That it exists, yeah.
But it would mean that it exists. Now, in practice, normally the way that we would prove anything like that would be by finding the algorithm.
By finding one algorithm.
But there is such a thing as a non-constructive proof that an algorithm exists. This has really only reared its head, I think, a few times in the history of our field, right? But it is theoretically possible that such a thing could happen. But there are some amusing observations that one could make. So there is this famous observation of Leonid Levin, who was one of the original discoverers of NP completeness, right? And he said, well, consider the following algorithm that, like, I guarantee will solve the NP problems efficiently, just as provided that P equals NP. Mm-hmm. Okay, here is what it does. It just runs, it enumerates every possible algorithm in a gigantic infinite list, right? From in alphabetical order, right? And many of them maybe won't even compile, so we just ignore those. Okay, but now we just, run the first algorithm, then we run the second algorithm, we run the first one a little bit more, then we run the first 3 algorithms for a while, we run the first 4 for a while. This is called dovetailing, by the way. This is a known trick in theoretical computer science. Okay, but we do it in such a way that whatever is the algorithm out there in our list that solves NP complete, the NP problems efficiently, we'll eventually hit that one, right? And now the key is that whenever we hit that one, by assumption, it has to solve the problem, has to find the solution. And once it claims to find a solution, then we can check that ourselves. Right? Because these are NP problems.
Yeah.
Then we can check it. Now, this is utterly impractical, right? You'd have to do this enormous exhaustive search among all the algorithms. But from a certain theoretical standpoint, that is merely a constant prefactor. Right?
It's at least possible.
That's merely a multiplier of your running time. So there are tricks like that one can do to say that in some sense the algorithm would have to be constructive. But in the human sense, it is possible that it's conceivable that one could prove such a thing via a non-constructive method. Is that likely? I don't think so. Not personally.
So that's P and NP, but the complexity zoo is full of wonderful creatures.
Well, it's got about 500 of them.
500. So how do you get? How do you get more? How do you?
I mean, just for starters, there is everything that we could do with a conventional computer with a polynomial amount of memory. Okay, but possibly an exponential amount of time because we get to reuse the same memory over and over again. Okay, that is called P space. Okay, and that's actually we think an even larger class than NP. Okay, well, P is contained in NP, which is contained in P space. And we think that those containments are strict.
And the constraint there is on the memory. The memory has to grow polynomially with the size of the problem.
That's right. But in P space, we now have interesting things that were not in NP, like as a famous example, from a given position in chess, does white or black have the win? Let's say, provided that the game lasts only for a reasonable number of moves.
Oh,
okay,
interesting.
Or likewise for Go. Okay, and even for the generalizations of these games to arbitrary size boards, right? Because with an 8x8 board, you could say that's just a constant size problem. You just, in principle, you just solve it in O of one time, right? Yeah. But so we really mean the generalizations of games to arbitrary size boards here. Or another thing in P space would be like I give you some really hard constraint satisfaction problem, like traveling salesperson or packing boxes into the trunk of your car or something like that. And I ask not just is there a solution, which would be an NP problem, but I ask how many solutions are there. Okay, that count the number of valid solutions. That actually gives those problems lie in a complexity class called sharp P, or like it looks like hashtag P.
Got it.
Okay, which sits between NP and P space. There's all the problems that you can do in exponential time. Okay, that's called exp. So, and by the way, it was proven in the 60s that exp is larger than P. Okay, so we know that much. We know that there are problems that are solvable in exponential time that are not solvable in polynomial time. Okay. In fact, we even know more. We know that there are problems that are solvable in n cubed time that are not solvable in n squared time.
And those don't help us with a controversy between P and NP.
Unfortunately, it seems not, or certainly not yet. Right? The techniques that we use to establish those things, they're very, very related to how Turing proved the unsolvability of the halting problem, but they seem to break down when we're comparing two different resources, like time versus space, or like P versus NP. Okay, but there's what you can do with a randomized algorithm, right? That can sometimes, has some probability of making a mistake. That's called BPP, bounded error probabilistic polynomial time.
Wow.
And then, of course, there's one that's very close to my own heart, what you can efficiently do in polynomial time using a quantum computer. Okay, and that's called BQP, right? And so,
what's understood about that class? Maybe as a comment.
So P is contained in BPP, which is contained in BQP, which is contained in P space. Okay, so anything you can, in fact, in something very similar to sharp P. BQP is basically, it's contained in like P with the magic power to solve sharp P problems. Okay, so
Why is BQP contained in P space?
oh, that's an excellent question. There is well, I mean, one has to prove that, okay?
Right.
But the proof, you could think of it as using Richard Feynman's picture of quantum mechanics, which is that you can always, we haven't really talked about quantum mechanics in this conversation. We did in our previous one.
Yeah, we did last time.
But yeah, we did last time. Okay, but basically, you can always think of a quantum computation as like a branching tree of possibilities, where each possible path that you could take through, the space has a complex number attached to it called an amplitude. Okay, and now the rule is, when you make a measurement at the end, you see a random answer. Okay, but quantum mechanics is all about calculating the probability that you're going to see one potential answer versus another one, right? And the rule for calculating the probability that you'll see some answer is that you have to add up the amplitudes for all of the paths that could have led to that answer. And then, that's a complex number. So that, how could that be a probability? Then you take the squared absolute value of the result. That gives you a number between 0 and 1. Okay. So, I just summarized quantum mechanics in like 30 seconds. Okay. But now, what this already tells us is that anything I can do with a quantum computer, I could simulate with a classical computer if I only have exponentially more time. Okay, and why is that? Because if I have exponential time, I could just write down this entire branching tree and just explicitly calculate each of these amplitudes, right? That will be very inefficient, but it will work, right? It's enough to show that quantum computers could not solve the halting problem, or, they could never do anything that is literally uncomputable in Turing's sense. Okay, but now, as I said, there's even a stronger result, which says that BQP is contained in P space. The way that we prove that is that we say, if all I want is to calculate the probability of some particular output happening, which is all I need to simulate a quantum computer, really, then I don't need to write down the entire quantum state, which is an exponentially large object. All I need to do is just calculate what is the amplitude for that final state. And to do that, I just have to sum up all the amplitudes that lead to that state. Okay, so that's an exponentially large sum, but I can calculate it just reusing the same memory over and over for each term in the sum.
And hence the P in the P space.
Hence the P space.
Yeah.
Yeah.
So what, out of that whole complexity zoo, and it could be BQP, what do you find is the most, the class that captured your heart the most? Was the most beautiful class? It's just...
Well...
Yeah,
I used as my email address bqpqpoly@gmail.com, just because bqp/qpoly. Amazingly, no one had taken it. Okay?
Amazing.
But this is a class that I was involved in, sort of proving the first theorems about in 2003 or so. So it was kind of close to my heart. But this is like if we extended BQP, which is the class of everything we can do efficiently with a quantum computer, to allow quantum advice, which means imagine that you had some special initial state, okay, that could somehow help you do computation. And maybe such a state would be exponentially hard to prepare. Okay, but maybe somehow these states were formed in the Big Bang or something, and they've just been sitting around ever since, right? If you found one, and if this state could be like ultra power, there are no limits on how powerful it could be, except that this state doesn't know in advance which input you've got, right? It only knows the size of your input. And then that's BQP/qpoly. So that's one that I just personally happen to love. Okay, but if you're asking like what's the there's a class that I think is way more beautiful than or fundamental than a lot of people even within this field realize that it is. That class is called SZK, or statistical zero knowledge. And there's a very, very easy way to define this class, which is to say, suppose that I have two algorithms that each sample from probability distributions, right? So each one just outputs random samples according to, possibly different distributions. And now the question I ask is, let's say distributions over strings of n bits, so over an exponentially large space. Now I ask, are these two distributions close or far as probability distributions? Okay. Any problem that can be reduced to that, that can be put into that form is an SDK problem. And the way that this class was originally discovered was completely different from that and was kind of more complicated. It was discovered as the class of all of the problems that have a certain kind of what's called zero knowledge proof. The zero knowledge proofs are one of the central ideas in cryptography. Shafi Goldwasser and Silvio Micali won the Turing Award for, inventing them. And they're at the core of even some cryptocurrencies that, people use nowadays. But their zero knowledge proofs are ways of proving to someone that something is true, like, that there is a solution to this, optimization problem, or that these two graphs are isomorphic to each other or something, but without revealing why it's true, without revealing anything about why it's true. Okay. SDK is all of the problems for which there is such a proof that doesn't rely on any cryptography. Okay. And if you wonder, like, how could such a thing possibly exist, right? Well, like, imagine that I had two graphs and I wanted to convince you that these two graphs are not isomorphic, meaning, I cannot permute one of them so that it's the same as the other one, right? That might be a very hard statement to prove. Like, I might need, you might have to do a very exhaustive enumeration of, all the different permutations before you were convinced that it was true. But what if there were some all-knowing wizard that said to you, look, I'll tell you what, just pick one of the graphs randomly, then randomly permute it, then send it to me, and I will tell you which graph you started with. Okay? And I will do that every single time. Right?
Let me load that in. Okay, that's I got it.
And let's say that wizard did that 100 times and it was right every time.
Yeah.
Right? Now, if the graphs were isomorphic, then it would have been flipping a coin each time. Yeah. Right? It would have had only a 1 in 2 to the 100 power chance of guessing right each time. But so if it's right every time, then now you're statistically convinced that these graphs are not isomorphic, even though you've learned nothing new about why they aren't.
So fascinating.
Right? So SDK is all of the problems that have protocols like that one, but it has this beautiful other characterization. It's shown up again and again in my own work, and a lot of people's work, and I think that it really is one of the most fundamental classes. It's just that people didn't realize that when it was first discovered.
So we're living in the middle of a pandemic currently.
Yeah.
How has your life been changed? Or no, better to ask, like, how has your perspective of the world changed with this world-changing event of a pandemic overtaking the entire world?
Yeah, well, I mean, all of our lives have changed. Like, I guess as with no other event since I was born, you would have to go back to World War II for something, I think, of this magnitude, on, the way that we live our lives. As for how it has changed my worldview, I think that the failure of institutions, like the CDC, like, other institutions that we sort of thought were trustworthy, like a lot of the media, was staggering, was absolutely breathtaking. It is something that I would not have predicted, right? I think I wrote on my blog that it's fascinating to like rewatch the movie Contagion from a decade ago, right? That correctly foresaw so many aspects of, what was going on. An airborne, virus originates in China, spreads to, much of the world, shuts everything down until a vaccine can be developed. Everyone has to stay at home. It gets an enormous number of things right. Okay. But the one thing that they could not imagine, is it like in this movie, everyone from the government is like hyper competent, hyper, dedicated to the public good,
Yeah.
right?
The best of
And
the best.
yeah, they're the best of the best. They could, and there are these conspiracy theorists, right, who think, this is all fake news. There's not really a pandemic, and those are some random people on the internet who the hyper competent government people have to, oppose, right? They, in trying to envision the worst thing that could happen, like, there was a failure of imagination. The movie makers did not imagine that the conspiracy theorists and the incompetents and the nutcases would have captured our institutions and be the ones actually running things.
So you had a certain.
Yeah.
I love
Yeah.
competence in all walks of life. I get
Yeah.
so much energy. I'm so excited by people who do amazing job, and I, like you. Well, maybe you can clarify, but I had maybe not an intuition, but a hope that government at its best could be ultra competent. What? First of all, well, two questions. Like, how do you explain the lack of confidence, and the other, maybe on the positive side, how can we build a more competent government?
Well, there's an election in 2 months. I mean,
But you have a faith that the election process.
it's not going to fix everything, but it's like I feel like there is a ship that is sinking, and you could at least stop the sinking. But I think that there are much deeper problems. I mean, I think that it is plausible to me that a lot of the failures with the CDC, with some of the other health agencies, even predate Trump, predate the right-wing populism that has sort of taken over much of the world now. And I think that it is very. I'm actually, I've actually been strongly in favor of rushing vaccines. I thought that we could have done human challenge trials, which were not done. Right? We could have had volunteers, to actually be get vaccines, get exposed to COVID.
So innovative ways of accelerating what we've done previously over a longer.
I thought that each month that a vaccine is closer is like trillions of dollars.
Are you
for
surprised
civilization and of course lives?
Yeah.
At least hundreds of thousands of lives.
Are you surprised that it's taking this long? We still don't have a plan. There's still not a feeling like anyone is actually doing anything in terms of alleviate like any kind of plan.
Well,
so there's a bunch of stuff. There's vaccine, but you could also do a testing infrastructure where everybody's tested nonstop with contact tracing, all that kind of stuff.
Well, I mean, I'm as surprised as almost everyone else. I mean, this is a historic failure. It is one of the biggest failures in the 240-year history of the United States, right? And we should be crystal clear about that.
Yeah.
And one thing that I think has been missing, even from the more competent side, is is sort of the World War II mentality, right? Yeah. The mentality of let's just if we can, by breaking a whole bunch of rules, get a vaccine in in even half the amount of time as we thought, then let's just do that because like we have to weigh all of the moral qualms that we have about doing that against the moral qualms of not doing it.
And one key little aspect to that's deeply important to me, and we'll go in that topic next, is the World War II mentality wasn't just about, breaking all the rules to get the job done. There was a togetherness to it. There's so I would, if I were president right now, it seems quite elementary to unite the country because we're facing a crisis. It's easy to make the virus the enemy. And it's very surprising to me that the division has increased as opposed to decreased. That's heartbreaking.
Yeah, well, look, I mean, it's been said by others that this is the first time in the country's history that we have a president who does not even pretend to, want to unite the country, right?
Yeah.
And I mean, Lincoln, who fought a civil war, said he wanted to unite the country, right? And I do. I do worry enormously about what happens if the results of this election are contested, and, will there be violence as a result of that? And will we have a clear path of succession? And, look, I mean, this is all we're going to find out the answers to this in 2 months. And if none of that happens, maybe I'll look foolish, but I am willing to go on the record and say I am terrified about that.
Yeah, I've been reading the Rise and Fall of the Third Reich. It's
Yeah.
a difficult. So if I can, this is like one little voice to put out there that I think November will be a really critical month for people to breathe and put love out there. Do not, anger in that context, no matter who wins, no matter what is said, will destroy our country, may destroy our country, may destroy the world because of the power of the country is. So it's really important to be patient, loving, empathetic. Like one of the things that troubles me is that even people on the left are unable to have a love and respect for people who voted for Trump. They can't imagine that there's good people that could vote for the opposite side. And that's...
Oh, I know there are, because I know some of them.
Yeah.
Right? I mean, it's still, maybe it baffles me, but, I know such people.
Let me ask you this. It's also heartbreaking to me on the topic of cancel culture.
Yeah.
So in the machine learning community, I've seen it a little bit, that there's aggressive attacking of people who are trying to have a nuanced conversation about things. And it's troubling because it feels like nuanced conversation is the only way to talk about difficult topics. And when there's a thought police and speech police on any nuanced conversation, that everybody has to, like in Animal Farm, chant that racism is bad and sexism is bad, which is things that everybody believes. And they can't possibly say anything nuanced. It feels like it goes against any kind of progress from my kind of shallow perspective. But you've written a little bit about cancel culture. Do you have thoughts that are
well, look,
to
say that I am opposed to, this trend of cancellations or of, shouting people down rather than engaging them, that would be a massive understatement. Right. And I feel like, I have put my money where my mouth is, not as much as some people have, but, I've tried to do something. I mean, I have defended, some unpopular people and unpopular, ideas on my blog. I've, tried to defend, norms of open discourse, of reasoning with our opponents, even when I've been shouted down for that on social media, called a racist, called a sexist, all of those things. And which, by the way, I should say, I would be perfectly happy to, say, if we had time to say, 10,000 times, my hatred of racism, of sexism, of homophobia, right? But what I don't want to do is to cede to some particular political faction the right to define exactly what is meant by those terms. To say, well, then you have to agree with all of these other extremely contentious positions, or else you are a misogynist, or else you are a racist, right? I say that, well, no, don't I, or, don't people like me also get a say in the discussion about, what is racism, about what is going to be the most effective to combat racism, right? And, this cancellation mentality, I think, is spectacularly ineffective at its own professed goal of, combating racism and sexism.
What's a positive way out? So I try to, I don't know if you've seen what I do on Twitter, but on Twitter, I mostly, in my life, I've actually, it's who I am to the core. Is like, I really focus on the positive, and I try to put love out there in the world. And still I get attacked. And I look at that and I wonder, like,
you too? I didn't know.
Like, I haven't actually said anything difficult and nuanced. You talk about somebody like Steven Pinker, who I actually don't know the full range of things that he's attacked for, but he tries to say difficult. He tries to be thoughtful about difficult topics.
He does.
And obviously he just gets slaughtered by
Well,
certain.
yes, but it's also amazing how well Steve has withstood it. I mean, he just survived an attempt to cancel him just a couple of months ago,
But
right? And
psychologically, he survives it too, which
yeah,
worries me because
he
I don't think
seems.
I can.
Yeah, I've gotten to know Steve a bit, and
Yeah.
he is incredibly unperturbed by this stuff.
That's
I admire that, and I envy it. I wish that I could be like that. I mean, my impulse when I'm getting attacked is I just want to engage every single like anonymous person on Twitter and Reddit who is saying mean stuff about me, and I want to just say, look, can we just talk this over for an
yeah.
hour, and then you'll see that I'm not that bad. And and sometimes that even works. The problem is then there's the 20,000 other ones,
Yeah.
right?
And that's not.
but
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 psychologically, does that wear on you?
it does. But yeah, I mean, in terms of what is the solution, I mean, I wish I knew, right? And so, in a certain way, these problems are maybe harder than P versus NP, right? I mean, but I think that part of it has to be for, that I think that there's a lot of sort of silent support for what I'll call the open discourse side, the, reasonable enlightenment side. And I think that support has to become less silent, right? I think that a lot of people, they sort of, like agree that, a lot of these cancellations and attacks are ridiculous, but are just afraid to say so, right? Or else they'll get shouted down as well, right? That's just the standard witch hunt dynamic, which, of course, this faction understands and exploits to its great advantage. But if more people just said, like, we're not going to stand for this, right? No, this is we're guess what, we're against racism too, but this, what you're doing is ridiculous, right? And the hard part is, like, it takes a lot of mental energy, it takes a lot
Yes.
of time, even if you feel like you're not going to be canceled, or you're staying on the safe side, like, it takes a lot of time to phrase things in exactly the right way, and to respond to everything people say. So, but I think that the more people speak up, then from all political persuasions, from like all walks of life, then the easier it is to move forward.
Since we've been talking about love,
Hmm.
can you? Last time I talked to you about the meaning of life a little bit, but
Mhm.
here it's a weird question to ask a computer scientist, but has love for other human beings, for things, for the world around you played an important role in your life? Have you? It's easy for a world-class computer scientist. You could even call yourself like a physicist. Everything to be lost in the books. Is the connection to other humans, love for other humans, played an important role?
I love my kids. I love my wife. I love my parents. Um, I am probably not different from most people in loving their families, and in that being very important in my life. Now, I should remind you that I am a theoretical computer scientist. If you're looking for deep insight about the nature of love, you're probably looking in the wrong place to ask me. But sure, it's been important.
But is it
Yeah.
is there something from a computer science perspective to be said about love? Is there or
Uh,
is that even beyond the realm of consciousness and
there
all
there
that?
there was this great cartoon. I think it was one of the classic XKCDs where it shows like a heart, and it's like, squaring the heart, taking the Fourier transform of the heart, integrating the heart, each thing, and then it says, my normal approach is useless here.
I'm so glad I asked this question. I think there's no better way to end it,
All
Scott.
right.
I hope we get a chance to talk again. This has been
Yeah.
amazing. Cool experiment to do it outside. And
Yeah.
I'm really glad you made it out.
Yeah.
Thank you
Well,
so
I
much.
appreciate it a lot. It's been a pleasure, and I'm glad you were able to come out to Austin.
Thanks. Thanks for listening to this conversation with Scott Aaronson. And thank you to our sponsors, 8 Sleep, Simply Safe, ExpressVPN, and BetterHelp. Please check out these sponsors in the description to get a discount and to support this podcast. If you enjoy this thing, subscribe on YouTube, review it with 5 stars on Apple Podcast, follow on Spotify, support on Patreon, or connect with me on Twitter at Lex Fridman. And now let me leave you with some words from Scott Aaronson that I also gave to you in the introduction, which is, if you always win, then you're probably doing something wrong. Thank you for listening and for putting up with the intro and outro in this strange room in the middle of nowhere. And I very much hope to see you next time in many more ways than one.